Welcome back to the DataProfessor YouTube channel. If you're new here, my name is Chanin Nantat Senamat, and I'm an Associate Professor of Bioinformatics. On this YouTube channel, we cover about data science concepts and practical tutorials. So if you're into this kind of content, please consider subscribing. So scatterplots help you to visualize the distribution of your data variables in a pairwise manner if you have a 2D plot. Today we're going to show you how you can use the plot function of the RBase to visualize the distribution of two variables. So without further ado, let's get started. So head over to the DataProfessor GitHub page and click on the code repository and then click on the plot scatterplot. Okay, and then you want to download both files, the input file, the data set that we're going to use today, and the code scatterplot.r file. So for example, click on the first one and then right click on the raw link and then save target as or save link as if you're using Chrome, and then do the same thing for the code. Right click, save target as or save link as if you're using Chrome. Okay, so I have already downloaded onto my computer. So open up your RStudio and then set your working directory to where the files are located. So let's have a look at the input data set. So it is a comma separated value file here, which we will import in just a moment. So click on your code file, and the input data that we're going to use today is based on the aromatase data set. So aromatase is a protein which is implicated in the development of breast cancer because it leads to the production of estrogen from androgens. And overproduction of estrogen will lead to tumor growth in the breast. And so therefore, scientists are focusing on how to prevent the overproduction of estrogen. And they discovered that if they develop inhibitors or compounds or molecules that could bind to aromatase, then it will lead to the reduction of the estrogen levels and therefore curb the development of breast cancer. So the data set that we're using today is coming from this research article. So let me show you. So this research article is entitled Exploring the Chemical Space of Aromatase Inhibitors. And so this paper was published 7 years ago in 2013. And it is one of our research group's publication where we were funded by the research grant of Mahidol University, where we investigated the chemical space of aromatase inhibitors in order to make sense of the molecular features that are giving rise to compounds being able to inhibit the aromatase protein, and so which will help in the development of novel breast cancer therapeutics. And so the data set is provided as a supplementary file. It is in Excel format, supplementary material 2. And so for the purpose of this tutorial, I have converted it into a CSV format. Okay, so let's load in the data and load it into the variable called aromatase using the read.csv function. And so you notice that there are a total of 973 molecules and a total of 20 variables. So let's use the view command to have a look at the data set before we begin. Okay, so notice that the first column is just the number. Second column is the class, or whether the compound is a steroid or non-steroid. Third column is the SMILES notation, and the SMILES notation is essentially a one-dimensional depiction of the chemical information or the chemical structure of the molecule. And the PIC50 is the biological activity of the molecule, which is measured by the biological assay. And Y label will be called either active or inactive, depending on whether the PIC50 value is above or below the bioactivity threshold. The threshold is set as 6. If it is above 6, it is classified as active. And if it is below 6, it is classified as inactive. And then the subsequent columns are the X variables, which are the molecular descriptors which describe the unique chemical properties of the molecule. So they comprise of molecular weight. The RBN is the number of rotatable bonds, number of cyclic ring, number of hydrogen bond donors, number of hydrogen bond acceptors. A log P tells about the solubility. TPSA is the topological polar surface area, which tells about the polarity of the surface area of a molecule. QM tells about the distribution of the charge in a molecule. Energy is the molecular energy of the molecule, because each atom has a finite energy, and so taken together in a molecule is comprised of multiple atoms, and therefore it has atomic energy. So bigger molecule, more energy. And then there are other parameters. Dipole moment tells about the distribution of the charge in a molecule. Homolumo and homolumo gap tells you about the distribution of the electron density. It is highly occupied or less occupied, and the gap between those two molecular orbital. And in columns 19 and 20 will be the article title and the reference in which the data was obtained from. So this was manually curated. Okay, so let's check out for any missing value, and there is none. So we can skip the following line of code. And then we're going to take the class label, whether it is steroid or non-steroid, and save it into class, because we're going to use this information to color the plots. So let's view the aromatase dataset again. So the second column is the class, steroid and non-steroid. So when we use the aromatase followed by the bracket, so the number on the left is the row and the number on the right is the column. So when there's no number here, it means that we want to select all rows. And if we specify the number to the right, it means that we want to select specific columns. Because we set it to 2, it means that we want to select only column 2. And then the next stage, we will have selected column 6, and colon would mean everything in between 6 and 18. So we're going to select column 6 through 18. And so these will essentially be here, molecular weight, RBN, until the column before the reference, which is homolumo gap. So this will represent the chemical properties of the molecule, which could be used in producing a prediction. And then we will combine the class label here of the steroid and non-steroid and combine it with the X descriptor to form aromatase 3, and then we're going to just rename it to DF, data frame. Okay, because we forgot to run the class. Oh, okay, forgot to run aromatase 3. There you go, and then rename it. Okay. Okay, and so we're going to perform the scatter plot using the plot function in R. And when we're using plot followed by the data frame name, it will produce all possible scatter plot between all of the variables in the data frame with one another. So in just a moment, we're going to see that here in the plot. So we see that there is, actually we can omit the class column here. So let's start from MW. So there is several, I think it's 13, right? All possible combination between each of the variables with one another. So molecular weight with RBN, molecular weight with number of cyclic ring, molecular weight with number of hydrogen bonds donor, molecular weight with hydrogen bonds acceptor, etc. And number of hydrogen bond donor with 8 TPSA, right? So you could read it by moving down the column and then moving sideways. And then you get to see the pair between the scatter plot here. So let's say that we want to change the color to blue. We add the color argument equals to blue. In just a moment, it will change to blue. There you go, it changes to blue. And let's say that we want to look at the distribution between molecular weight and A log P, which we commonly use in our research study to look at the chemical space or the chemical universe spanned by the compounds. So more or less it's just an exploratory data analysis to see the relative distribution of the compound in our data set. So we could specify that by using the plot function and then df $MW. By putting the $, it means that we're going to select a particular variable inside the data frame of df. And so df $MW means that we're going to select specifically the MW columns. And when I enter that into the terminal console of R, I get only the values coming out of this MW column. And df $A log P will give me all of the values of the A log P column. And so plot MW and A log P will give me the distribution of MW and A log P shown here. Okay. So notice that they are open circles, and I will show you later on how you could modify the symbols to be closed circles, plus, minus, X, etc. Okay, and here we're going to add colors to the plot. So all of the data samples here are colored in black. So let's say that we want to color each of the data sample according to whether they are steroid or non-steroid. And we could do that by first applying the factor function, by specifically stating that if we want to have steroid, we will have to color it as blue. And if we have non-steroid, we're going to color it as red. And then this would then be assigned to the color column, which is newly created here into the DF data frame. So essentially here, we're going to create a color column, which will contain the value of blue or red, depending on whether it is a steroid or non-steroid. So a steroid will be colored as blue and a non-steroid will be colored as red. So let's run this code here. Okay, and then we're going to run the plot. Okay, there you have it. You have the coloring of the data samples according to whether they are steroid or non-steroid. But also notice that the data samples are in closed circles created by the PCH argument, and it is equal to 16, which means it is a closed circle. There are several numbers in which you could modify this to. I will cover that shortly. So df $color is either blue or red, which is created by this function. Okay, and then we're applying the asCharacter function as well, because the type of df color would be integer, but when we say asCharacter df color, and then we're gonna look at the type of that, it will be character, right? So if we don't convert it into a character, it will be treated as an integer, which is wrong, and it will give you an error. Okay. Okay, so R has 657 colors by default using the colors function. So if you type in colors, you get all 657 colors, right? And you could choose one that you think looks nice. You could try it out. And so if I say color equals to red, it will create the red dots here. I mean the red circles here. Blue, green, purple, or I could use orange, red 3, right? Or it could be anything in here. It could be what? Sea green 3, right? Or you could also use your hex color code as well, right? Hashtag FF0000, and then you would get red, right? This is normally used for HTML coding, for creating websites. So if you're familiar with hex color code, then you could use this here as well. For those familiar with the RGB color code, then you could also use it here. So by default, RGB has the range of 0 and 1. And then we could use the maximum argument to be 255 because this is the format that we are familiar with, having a scale of 255. And so if RGB is 25500, this corresponds to red color because RGB stands for red, green, blue. So if you have the maximum value in red, then it becomes red. If you have the maximum value in green and the other values are 0, then it becomes green. Right? So the intensity of the color depends on the RGB color code. And here you can specify the RGB as the argument value of color. Okay, now let's hop on to the symbols. So by default, the PCH will be assigned as 1. So they are the open circle. But if we assign it to become 2, it will become a open triangle. If it's 3, it will become a plus symbol. 4 will be X. 5 will be diamond. 16 will be closed circles. And if we have 17, then it repeats to become closed triangles. Okay, so you could use the one that you like. And I like the filled circle symbol, so I'm gonna fix it to 16. I'm gonna color it to be orange, red 3, right? And then you could also use the RGB color code scale as well. But then notice that data samples are pretty cluttered together. I mean, it's a bit difficult to see when the density is really high. I mean, one data sample stacking on top one another. So what can we do about that? We could add transparency to the color. So we could use the scales library. Let's do that. And here we set the transparency to become 0.3. And notice that the color then becomes a bit more translucent. And when it's 1, it's a solid color, right? And then if you say 0.9, it becomes slightly translucent. 0.8, 0.7, 0.6, 0.5. So I'm showing you gradually becoming more translucent. 0.4, 0.3, which I like to use, 0.2, 0.1, okay? Right, so something in between 0.2 and 0.3 I think is the sweet spot. Okay, so you could also, instead of using this one, you could use the RGB color scale as well. And then number here will be the transparency. You could make it 100. You can make it 255. Then it becomes a solid color. I use 75, which is roughly 0.3, right? 75 divided by 255. Yeah, roughly 0.3. And then you could also color it according to the class of being a steroid or non-steroid, and using a transparency of 0.3. So right here, looks pretty good. So now let's hack the code a bit. So if you want to add the X label, you could do it using the XLab argument. And if you would like to modify the Y label, you could use the YLab argument. So let's run this block of code here. And the AB line will allow you to add a trend line to your scatter plot, which also comes in handy. So recap, plot function used to create the scatter plot of the molecular weight, because we're selecting by using the $, specifically the molecular weight column from the data frame DF, and then we're selecting the A log P column from the DF data frame, and then we're assigning PCH to become 16, which is the closed circle, and the color argument is equals to alpha, because we're going to use the alpha transparency. We're going to use the color of red. We're going to use the transparency of 0.3, which could be in the range of 0 to 1 depending on the translucence that you would like to have. And the X label is in XLab, Y label is here in the YLab, and then you could adjust the label for the X and Y axis to your liking. So font.lab equals to 2 will make the X and Y label to become bold, right? And AB line function will allow it to add the trend line. Okay, so let's now hop on to creating a multiplot figure. So you're going to use the command PAR, and you're going to use the argument mfrow. And if the value is 2, 2, it means that there is 2 rows by 2 columns. And so first you have to run this par command, right? Let's do that. And then we're going to run the plot commands in sequential order. 1, 2, 3, 4. Okay, there you have it. You get a 2 by 2 figure. And let's say that you want a 3 by 1 column figure. Then you modify 2, 2 to become 3, 1. So as you can see that the first argument tells you the number of rows, and the second argument tells you the number of columns. So 3, 1 would mean 3 rows, 1 column. So let's do that. Run this one. Run the first par command, and then the first plot, second plot, and then the third plot. So then you have a 3 by 1. Okay, and then the same concept, if you want to have a 1 row by 3 columns, you adjust it to be 1, 3. Okay, and if you want to switch the order of your scatter plot, you could do that as well, switching A log P and MW. Okay, and the final step is you want to save your plots onto a file. So here we're going to save it into a PDF file. So what you need to do is use the PDF function followed by the name of your PDF file, followed by inserting your plot function here. So all of the plot commands that you want to run, and then followed by saving it off by using the dev.off function. So having the dev.off function is kind of like confirming whether you want to save the file or not. Okay, so PDF is kind of like telling it to save in a PDF format, and then plot.pdf is the name of the file that you would like to save. Dev.off is confirming that you want to save the file. Okay, so if we use this block of code, then it means that we're going to create a file of the A log P and MW scatter plot, and it looks like this. Okay, the PDF file. And so if we want to save it as a multiplot figure, then we're going to use the same concept by just replacing the contents here with the contents of the par command along with the subplots 1, 2, 3, 4. So if we want to create a 1 by 3 figure and saving it, we're going to use this block of code. We're going to run the PDF function par plot 1, 2, 3. And if we don't do anything, let me click on the refresh. And let's click on the file. The file is created, but the content is not yet saved into the file. And so what we need to do is signing it off by running the dev.off. Now you see that the size changes to 21.3. Now let's click on the file again. Okay, now the file content is saved into the file. Okay, and that's all there is to saving the file as the PDF. So congratulations, you have now created your scatter plot in R, and you can also save it as the file. So don't forget to compile your progress in your data science portfolio. So you could modify the data set to be using the one that interests you, but the key to learning data science is to practice, is to do data science. So if you have some interesting data set that you would like me to use in the future tutorials, let me know in the comments. Thank you for watching. Please like, subscribe, and share, and I'll see you in the next one. But in the meantime, please check out these videos.